Hello everyone, my name is Brian Harrison from 11 IDEA, and today in this video I'm going to teach you a little bit about thermal physics. So basically, thermal physics is the science of everything related to heat and temperature. And here are some of the terms that we will come across when we are dealing with thermal physics. First is heat. Heat is simply the transfer of energy. Then there is the kinetic molecular theory. So there is more than the what I written with in the kinetic molecular theory, but for now, for this this is to just to reinforce the next definition. So I'm going to only say one of the main point, which is kinetic molecular theory states that gas particles are in constant motion and exhibits perfectly elastic collision. So all those particles are always moving and they bump into each other all the time. Next is thermal energy. Thermal energy is the energy generated and transferred by heat, which refers to an internal energy or average kinetic energy caused by the collision of and movement of molecules. So we know that the particles are always in constant motion. So due to that motion, of course, we are going to have kinetic energy, and that average kinetic energy is what we call thermal energy. And thermal energy can be measured by temperature. So temperature is the measure of thermal energy being transferred, which refers to the degree of hotness or coldness of a body. And the way you measure temperature is by using something called a thermometer. Now, thermometer, if you categorize, there is two categories. First, you can categorize it by according to its usage, which will be categorized into three. Let me just move this. Which is clinical thermometer, laboratory thermometer, and atmospheric thermometer. Each usage is different from each other. Next, you can also measure from the liquid that is used. We have alcohol thermometer and mercury thermometer. Now, how do thermometer works? So you pay attention that there is a liquid inside. This liquid will expand and contract depending on the temperature that is being measured. If the temperature that is being measured is 40, this liquid will then expand, the volume will expand until it will reach the point 40. And that's how you know that the thing that you are trying to measure is 40 degrees. So by measuring temperature, there are 5 units of temperature that we can use. First and the most common is Celsius, or with the unit degree Celsius, invented by Anders Celsius. With the freezing point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. So the range, which is from freezing point to boiling point, is 100. Next, we have Fahrenheit, which the unit is degree Fahrenheit, which is invented by Gabriel Daniel Fahrenheit. The freezing point of water 32 Fahrenheit, boiling point 212 degree Fahrenheit, with the range 180. Next, we have Kelvin. So look carefully that Kelvin is not measured by the unit. Don't have this small thing. So you have to make sure whether or not a unit have the degree symbol or not. So if Kelvin, there is no symbol, it's just K. Invented by William Thomson, with the freezing point of water 272 Kelvin, and the boiling point 373 Kelvin, with the range 100. The range is 100. Kelvin is also the standard unit for temperature. Next, we have Réaumur. So pay attention to the unit. Don't confuse it with Rankine. The inventor of Réaumur is René Antoine Verschaal de Réaumur. With a freezing point of 0 Réaumur and boiling point of 80 Réaumur, the range is 80. And lastly, Rankine. The inventor is William John McCorn Rankine. Freezing point of water is 492 Rankine. The boiling point of water is 672 Rankine, and the range is 180. So, some people ask, like, is there a possibly a lowest temperature or a highest temperature? A lowest temperature is actually possible. The lowest temperature means that the particles exhibit the least motion, or it's basically it physically cannot go have even less motion. That's the most minimal motion that it can exhibit. And this temperature is in 0 Kelvin or negative 273.15 degrees Celsius. And it is often called absolute zero. And we haven't gotten to absolute zero. It is technically impossible, but we have come very close. We have reached 0.00 something 1 Kelvin and never absolute zero. Now, we can convert between the units of temperature. For example, I have degrees in Celsius, but I want to know what it is in Fahrenheit. So I can use this as a formula, which is the temperature of whatever scale minus the freezing point of that scale per the range of that scale equals whichever you want to convert to. So for example, I want to convert from Celsius to Fahrenheit, I can write temperature in Celsius minus the freezing point per the range. The freezing point is, I can just instantly write 0. The range is 100, will be equal to temperature of Fahrenheit minus the freezing point of Fahrenheit is 32 divided by the range is 180. So let's try some example questions of conversion between units of temperature. First, we have 457 Rankine to Kelvin. So here I have the table to assist you guys so that it's slightly easier for don't need to move back and forth from the video. So 400, the temperature of the temperature in Rankine is 457 Rankine. So we write it as 457 minus the freezing point is 492 per the range is 180 equals temperature in Kelvin minus 273. Sorry, that's a typo. 273 per 100. So temperature of Kelvin, you can write it as 100 divided by 180 multiplied by 457 minus 492 plus 273, which is equal 100 times 457 minus 492 divided by 180 plus 273. So you should get the answer is 253.55 until infinity Kelvin. Next, let's try the next is 105 Celsius to Fahrenheit. So 105 Celsius minus the freezing point is 0 per 100 is equal to Fahrenheit. Temperature in Fahrenheit minus freezing point is 32 and the range is 180. So temperature in Fahrenheit will be 180 times 105 per 100 minus a plus 32, which is 221 degree Fahrenheit, right? Next one, 95 Kelvin to Raymore. So 95 minus the freezing point 0. No. Freezing point 273. Again, that was a typo. 100 to Rankine Raymore. Temperature in Raymore minus 0 per 80. Temperature in Raymore, that means is 80 per 100 multiplied by 95 minus 273, which is we get your answer is negative 142.4 degrees Raymore. Next, let's say we have a thermometer, but there is no indicator. There's only the liquid inside. So how can we determine the temperature when using this thermometer? So we actually have a formula here for unmarked thermometer. So T accent and T is both temperatures. L accent is the length of the thermometer when the temperature is at T accent, and also L is the length of thermometer when the temperature is at T. Next, we have FP is the freezing point, and FPL is the length of thermometer at the freezing point. This is kind of hard to understand if it's only the formula, so let's try some questions. So length at 0 degree Celsius is 2.6 centimeters. 0 degree Celsius is the freezing point of water. So we can write the length FPL is 2.6 centimeter. Next, we have temperature 100 Celsius. And when the temperature is at 100 Celsius, the length is 17.4. So L is 17.4 centimeter. So they ask, what is the length at temperature? The second temperature is 58 Celsius. So what is the length? So we can just input everything. T accent 58 minus 0 per 100 minus 0 is equal to L accent minus 2.6 per 17.4 minus 2.6. So L accent is equal to 58 times 17.4 minus 2.6 per 100 plus 2.6. And putting it into your calculator, you should get, if I'm not wrong, at least, you should get 11.2 centimeters. There. That's the length when the temperature is at 58. Next, a little bit more tricky. It's a question. It's a long question. Tom ordered a thermometer online. However, he received a defect which still doesn't have any numbers or indicators printed on it. Tom placed the thermometer on ice water and measured the length to be 1.3 centimeters. So on ice water, that means it's at a freezing point. So freezing point length is 1.3 centimeter. He then left it at his room with the AC set on 24. So the next temperature is 24 Celsius and measured 4.7 centimeters on the thermometer. So length is 4.7 centimeters. Next, he then made some coffee and dipped the thermometer to the coffee, and he measured the length to be, the second length is 12.2 centimeters. How hot is the coffee in Fahrenheit? So it asks the temperature but in Fahrenheit. But this one actually is Celsius. So there's two ways that you can do this. You can first change this into Fahrenheit, and after you change to Fahrenheit, you put it into the formula, or you can just use the formula first and put it into the change it into Fahrenheit, whichever you are more comfortable with. For me, I will put it to the formula first. So T accent is unknown minus 0 Celsius per T is 24 minus 0 will be L accent is 12.2, FPL is 1.3 per 4.7 minus 1.3. So T accent will be 12.2 minus 1.3 per 4.7 minus 1.3 times 24. And into the calculator, you should get 76.9 degrees Celsius. So converting this, 0.9 minus the freezing point per range is 100 will be equal to temperature in Fahrenheit minus 32 per 180. So temperature in Fahrenheit will be, let's just move my face, 180 per 100 times 76.9 plus 32, and that gives you 170.42 degrees Fahrenheit. There we go. Right. So next, we're going to try to learn about calorimetry, which is the science of measuring the amount of heat released or absorbed in a physical or chemical system. To calculate calories, there are four main units that we can use. First is calorie with a small c. This is very important in the unit and also in the name. It is small calorie. Usually, the name is small calorie when you want to say it out loud. Well, here you see there is the same name, but with capital letter is big calorie. So what is the difference? Here, calorie is the 1 calorie is the amount of heat to raise the temperature of 1 gram of water by 1 degree Celsius. While here, calorie or kilocalorie, kcal, is equals to 1000 calorie or is the amount of heat to raise the temperature of 1 kilogram of water by 1 Celsius. Next is joule. Joule here is the amount of heat to raise the temperature of 1 kilogram water by 1 Kelvin. So you look at this, these two are actually the standard unit of their respective thing measurement, whatever we want to say. So that means joule here is also the standard unit for calorimetry. So you can convert joule between joule and small calorie, which is 4.184 joule is equal to 1 calorie. Then the last one, which is also the most rare, I guess, which is the least common, is the British Thermal Unit, or BTU, which is the amount of heat needed to raise the temperature of 1 pound of water by 1 Fahrenheit. So to calculate the calories, there's this formula that we use, which is the amount of heat needed to raise or lower the temperature of a given mass of substance by a certain temperature. So here we have C, which is specific heat capacity, and different substances will have different specific heat capacity, and this specific heat capacity is needed to calculate the total heat that we need. So the formula is total heat is equal to mass times C times delta T, or delta T is difference in temperature. And here are all the units. Also, you look at this, there's J per kg K, also J per kg degree Celsius. These two are actually interchangeable. So for example, we have a given J per kg K, we can change it by using J per kg delta Celsius if the given in the question is using Celsius. So let's try the question. So how much heat would you need to get 5 kilograms of water from 15 Celsius to 85 Celsius, considering the specific heat capacity of water is 1486 joule per kg K. So we are using Celsius, so this one we can change as the specific heat capacity as 1486 joule per kg delta Celsius. The mass is 5 kilogram. The difference in temperature is 85 minus 15 is 70 Celsius. So we get the total amount of heat is 4186 times 5 times 70. Putting it into the calculator, 4186 times 5 times 70 equals 1465100 joule, or you can change it into 1465.1 kilojoule, right? And latent here next we have latent heat of vaporization and fusion. So we already know if we want to increase and decrease temperature, we need to use the specific heat capacity. But latent heat of fusion and vaporization are used to change between one state to another. If fusion is to change between solid and liquid. Here it says the latent heat associated with melting a solid into a liquid or freezing a liquid into a solid. Well, the latent heat of vaporization is the latent heat associated with condensing gas into liquid or vaporizing a liquid into gas. And each of them follows this formula, which is the total amount of heat we write at LF and LV is equal to mass times the specific latent heat of fusion or the specific latent heat of what's that called? Vaporization. So let's try. This is the last question that for today is quite long. Let's start. Dorothy is very bored. She's very bored, in fact. She's so bored, in fact, she's trying to attempt boiling of all 1.3 kilogram of her ice in her freezer from -4 Celsius. So we know that the mass of ice is 1.3 kilogram, and the temperature of ice is -4 Celsius. To do so, how much heat must be needed considering the specific latent heat of fusion? So LF is 334 kilojoule, or we can convert that into joule by times 1000. 334 times 10 to the power of 3 joule per kilogram. Its specific latent heat of vaporization, LV, is equal to 2260 kilojoule. Turning that into joule is times 10 to the power of 3 joule per kilogram. The specific heat capacity of ice is half of water's, so sea ice is sea water divided by 2. And lastly, sea of water. Specific heat capacity of water is 4186 joule per kilogram Kelvin, but here we have Celsius, so we can just write it as Celsius. Okay, so first, to get the total amount of heat that we need to calculate each step. So the first step we need from boiling is to get the ice to the into 0 Celsius. So from -4 to 0 Celsius, let's just say is 4 Celsius. So the Q of ice, we can write it as 1.3 times delta T is 4 times the latent heat of, the specific heat capacity of ice is 4186 divided by 2. So putting that in, we get 10883.6 joule, or I can just write it as 10.9 kilojoule to make it more simple. Then next is turning the ice into water, so latent heat of fusion is 1.3 times the specific latent heat of fusion is 334 times 10 to the power of 3. So we get 1.3 times 334, 10 to the power of 3. We get 434,200 joule, or 434.2 kilojoule. Right. Then next, we have water. Now we have water in 0 Celsius, and we want to get it all the way up to 100 Celsius. So the difference in temperature is 100 degrees. The Q of water now is 100 times 1.3 times the C of water, 4186 equals 544,180 joule, or we can just write it as 544.2 kilojoule. And finally, we turn this water into, we boil this water into gas. So we use the latent heat of vaporization, which is 1.3 times 2260 times 10 to the power of 3 joules, which is 1.3 times 2260. We get 293,800 joules, or just 2938 kilojoules. Adding that together, the total heat needed to turn -4 degrees ice into to boil them all into gas is first is 10.9 plus 434.2 plus 544.2 plus 2938, which is the total is we get 3927.3 kilojoules. So that's our final answer. So that's the last question, guys. Thank you for watching this video till the end. Hope you guys find this video entertaining and also educational. And thank you for watching. Goodbye.